Our next speaker is Cas. Cas is doing a master in Nijmegen. Is doing a master's of the mathematical foundations of computer science. So they've been researching recursion schemes, data type generic programming, the applications of category theory in programming language design. And they've been working with Haskell for 6 years now, mostly in the academic sector so far. So it's their first talk actually to a non-academic audience. A special applause for that. So today's talk is about structured traversals, and to put this into different terms. So if you know what a fold is for lists, what about folds for more generic data types, like for example an abstract syntax tree?
All right, thanks Franz for the introduction. Let me reset the timer. Okay, so basically the schema that the talk will follow is we will motivate the idea behind this first on the basis of code, then we will go to category theory, look at what happens there, and then go back to code. Okay. Oh, wait. All right. Like, first off, some notes about the language that you will see here. It's Haskell with some extensions. Some are for readability. Some are actually for saving space on the slides. And we will also be using some limited dependent types and type level programming to do the mutually recursive part, which is the second part of the talk. And if you haven't seen lambda case yet, it's a really cool extension which lets you pattern match in a lambda, and we will see this extensively on the slides. And I will also be writing composition in diagrammatic order, which means basically F before G, because there will also be diagrams with arrows, and I just find it to be more legible to have function composition go from left to right. Okay, so we will first look at the case of single recursion and then generalize. Here are two functions which basically do recursion over a list. And if we look at them a bit, we see there's some sort of structural similarity going on. So we pattern match on the list, and then we recursively call the function on the rest of the list, and then we combine the recursive result somehow with the element, with the head of the list in this step. And so the question is this a design pattern? And some people may know it as such, but this has been pointed out before. Design patterns are kind of a poor person's abstraction. We want to actually recognize the common structure, what's going on, and then find the correct abstract notion and somehow treat this design pattern, quote unquote, as a first-class citizen. So, like, what is actually going on in these kind of traversals, like that we saw, like length and filter and a bunch of other ones, is you can think of it as replacing the constructors of your data type with functions. So the list has the cons constructor and the nil constructor, and traversals have a value for the base case and then a value for combining the steps of the previous results of the recursion with the current head element. And we will look at an example evaluation of how we kind of crush a list data structure, which is I'm basically folding this tree where I'm filtering out where I'm keeping only the even elements. can see the 4 is kept. The 3 will not be kept, so I will like concatenate an empty list to the recursive result. And here again, collect this one, and then finish off with a list. So that's basically this concept of replacing constructors with functions. And basically you're replacing kind of the data structure with the call structure, actually, the call structure of the recursive functions that's going on. And so what we can see from this is that even though we define these functions recursively, what they're doing can be understood non-recursively by factoring out what happens in the recursive step from the actual recursion that's going on, because that is basically derived from the structure of our data structure. Yeah, so another way to write the list data type that you may have seen is with GADT syntax, where we kind of actually write the constructors as functions that take arguments and go to the data type. So this is one way of looking at constructors that actually makes them look more like those functions that we said replace the constructors. And actually, in this talk, I will be rewriting things a lot to show how they are similar to other things. So this will be a common theme in the presentation. Yes, so we have a function here, lowercase list, and this one takes, yeah, it has 2 arguments, the way that the data type list has kind of 2 constructors. And if we squint a bit at the types, then we see this common structure. So in every place where we have list A in the declaration of the data type, in this fold for that data type, we have a value B, which is the final value that we're like folding the data structure into. And so, yeah, basically we're getting an idea that what's going on, the structure of the recursion can be derived from the structure of the data type. And this basically is now a function that, yeah, that takes these 2 parameters that are the functions that are replacing the constructors and factors out the recursion. And I define this with a local function, so I don't have to keep giving these functions through as arguments. All right. So with this function that I've defined now that factors out this recursion, I can redefine my length function that I previously defined recursively as using this kind of generic recursion scheme, and just give it as parameters the thing that I want to replace the nil constructor with and the thing that I want to replace the cons constructor with. Okay, let's look at an expression data type. We have a literal and plus, just so this is like a very simple expression data type. And I've again written it in GADT syntax. This is a language extension, by the way, that you can turn on. And here again, we have 2 functions as parameters that will replace the 2 constructors of the expert data type. And yeah, here you see where we do the recursive calls to factor out the recursion from the applications of this fold. Okay, so we've seen kind of that if we are given such a data type, we can really easily come up with the abstraction for it. Oop, yeah. Wait, did I skip a? No, okay. But we don't really, like, we want to understand actually what's going on a deeper theoretical level. And we also don't really want to have to write these functions ourselves. Basically, we never want to write boilerplate code. And that's why we will basically now do a little excursion into the theoretical foundations. And actually, this is an approach that I take generally to applying category theory to programming language design, which is you take a programming language, you find out what the already existing theoretical notions are, then you look at those notions in the abstract theoretical field, you see what's possible there, and then you try to translate it back into the programming language. So yeah, you kind of go from programming language to category theory and then back to programming language. And on the way, you, for some reason, you have to write a compiler to actually turn it into code, because in maths you can just say that some things are given, but then the compiler bugs you because it can't actually execute that thing that you know should exist. All right, I will introduce just enough category theory to actually illuminate what's going on. And please stop me if I'm going too fast or too slow, I don't know. Oh, actually, yeah, maybe I should get a view of the audience. So who here has had some experience with category theory? All right, okay, I think the title of my talk already did a nice pre-selection, so I'm not going to have to explain too slowly then, I guess. Okay, so a category C consists of a collection, and I'm going to be a bit pedantic about demarking when we are talking about objects and when we are talking about arrows, because in category theory we often like to identify like this C with like we kind of don't specify if we're talking about objects or arrows sometimes, and I think that's a bit annoying. So yeah, I will be a bit pedantic, at least in the beginning. We have objects and arrows between them, and in such a way that we can compose arrows. And for every object, there's an identity morphism going from that object to itself. Composition is associative, so if I do F, then G, then H, that's the same as doing F, then G, then H. And we have unit laws. So if I go do the identity arrow on A and then go via F to B, it's the same as going from A to B via F directly. Or if I go from A to B and then take the identity arrow on B, it's the same as just going from A to B via F. I will introduce the notion of isomorphisms. So if we have two objects A and B in a category C, then we say they're isomorphic via an arrow F. If there exists a G, so which goes from B back to A, which is both a left and a right inverse. And what that means is if I first take the identity, so all the diagrams that I will show on these slides are meant to be commutative. That means that any path that I take, that I can take via these arrows, is equal to any other path. So here we see if I go from the identity arrow A to A, it's if I go from A to A again via the identity arrow, it's the same as taking a detour to B via F and then going back from G to A, and the same if in B I go to A via G and then back to B via F, it's the same as just taking the identity arrow on B. And this can be summarized in a small diagram like this, but I think splitting it up like this is sometimes more illuminating. It's actually sometimes hard to choose how to split up your diagrams, but we will see that later in a bigger diagrammatic proof. Okay, then now I will introduce the concept of functors. And so we saw that categories have arrows between objects in those categories, but a natural question that might arise is if I look at kind of the category, is there such a thing as a category of categories? And it turns out, yes, there is, and the morphisms there are functors. And functors have the functor laws, which you might know from Haskell. Another way to actually express the functor laws is to say that commuting diagrams are preserved. And this actually gives you the other property that identities and composition are preserved. Like if you look back at how we defined the identity, you can define it as a diagram, and then the fact that that diagrams are preserved gives you the fact that identities are preserved. So yeah, basically it means we can go from some category C to some category D, and we will kind of find that diagram again there. All right. Yes. And often the way that you define a functor on arrows kind of follows naturally from the way that you choose to define it on objects. So I will mention some functors soon, and I will only mention how they are defined on objects. And yeah, sometimes the way that they're defined on arrows is left as an exercise to the reader. And we're going to basically, for the rest of this talk, look at the special case where the origin and the target category are the same. And then functor f is called an endofunctor. All right. Now we're going to look at another theoretical notion, which we're also going to need, which is called, sometimes called polynomial functors or the functor kit. And so the identity that basically sends objects to themselves, and as I said, I don't say how it's defined on arrows, but that's kind of follows from the definition on objects. So this is the functor. You may have seen this in Haskell as well. It exists as in the functor type class. You also have the constant to a functor, which basically, given any other object x in some category C, just maps that object to a. And yeah, categories can have products and or co-products. Products you kind of know like as product types, like tuples. Products, co-products are kind of like disjoint unions that where the elements are identified by a tag. You can think of either in Haskell as an example of a co-product. And basically, I can construct new functors from constituent functors in C by taking their co-product, and this will then be a functor in the product or the co-product category respectively, which we construct from these constituent categories. And yeah, we will see why this is useful later. Okay, now I will introduce the biggest, the most crucial notion of the talk, and that is algebras. So if I have an endofunctor in a category C and an object A in C, then if I have a morphism that goes from f of A to A, so the image under the functor of A back to that object A, then this construct is called an algebra, and the object A is called the carrier of the algebra. And basically, the algebras over a functor f again form a category, and the composition of two algebras, so these are now objects, the composition of these two things is a commuting diagram. So this is kind of a thing to get used to in category theory, that arrows are often not functions. They can be different things. And so the way that you would think about this actually is, okay, you have like a carrier A together with the morphism f8 to A, well, let's call it phi. That's your object A, or like your starting object. And then you have such an algebra again on object B, and the morphism from f of B to B called psi. That's like your target object. And then you have an f that goes between the carriers of these two algebras. And that's kind of the function component of that morphism. But because the morphism is actually a commuting diagram, the whole thing is kind of this function plus a proof obligation that these two, like if I go this edge, if I take this path in this diagram, it's the same as taking this path. So yeah, that's kind of a thing to keep in mind when you're going into category theory from a Haskell perspective. Arrows really are not functions, or they're often much more than just functions. And so sometimes categories can have an initial object, and an initial object is an object that from which there exists exactly one arrow to every other object in the category. So we have existence and unique existence. And yeah, this will actually also, the uniqueness will be important in some diagrammatic proof that we're going to be doing later. So yeah, given any other algebra with a carrier B, you can define this morphism. All right. Now we're going to use the concept of isomorphism that we defined earlier to look at Lambek's lemma, which says that if a functor f has an initial algebra, so we said an algebra from which we have a morphism to every other algebra, then the carrier of the algebra is isomorphic to f of a via the morphism. And here is the slightly more complicated proof. Okay, so basically we're going to want to have an isomorphism, a commuting diagram that where a goes to a on the lower edge via the identity, and f of a goes to f of a via f of the identity on the top edge. That's what it means to be the identity morphism in the category of F algebras. Okay, so we know there is a unique morphism. So yeah, the trick is to actually like take the F image of this algebra. So we apply F on top of the already existing F, and then we know there exists a morphism from A to F of A. And then we said on the lower edge, we want to go from A to A. Now we are at F of A, and we know a morphism that goes from F of A to A. And that morphism is alpha. So I'm now going to continue constructing this edge by putting alpha from here to A. And yeah, so basically this diagram commutes. And now what I need to show is that kind of this edge is equal to the identity. And the way to do that is to notice that we know an edge, or we know an algebra that goes from f of a to a, which is just the identity morphism. But because there is exactly one, there's exactly one edge from every. So there's exactly one morphism from an initial algebra to every other object, from initial object to every other object. We know that this composition here has to be equal to the identity. And because of that, basically we can prove that that A is isomorphic to f of A via alpha, since basically alpha. So from f of A, we go via alpha and then back to f of A, and that gives us the identity. And if we go from f of A to alpha, then that's also equal to the identity on the other object. Okay, and so the thing to know about the initial algebra is that it is the least fixed point of the functor f, and this is in the sense like least from where the term least here derives from the notion of initiality. Okay, so we wanted to have so we said, okay, so we said f of a is isomorphic to a via alpha. So we know there must exist an inverse to alpha, alpha to the minus one. And because of the commutativity of this diagram, we can give a recursive definition of this, because this edge is the same as so taking yeah, taking this edge is the same as taking wait, all right, no, sorry. We wanted to get a recursive definition for H. So H was the initial morphism that we're given, but like in category theory, we're just like this kind of, it's not really constructive in a sense. We've just proved that it always needs to exist for an initial object, and this edge H, we can take it by going basically via alpha -1, then f of H, and then psi in the target algebra. And because the diagram commutes, this kind of gives us something that looks like a recursive definition. And we will hold on to that because basically now we're going back to Haskell. Sighs of relief. Yeah, okay, so now we need to translate what we saw in category theory back to what's actually happening in the code. We will see that the recursive data types that we looked at earlier, so expression and list, they correspond to fixed points of associated functors, which we call structural, shape, or base functors. And those fixed points are the carriers of the initial algebras. Then we will see that the business logic of the traversals, so what kind of happens in the recursive steps, the functions that replace the constructors, these correspond to algebras over this structural functor. And the unique morphism that we get from the initial algebra to any other algebra B is the fold function that we were looking for, that we were searching the theoretical equivalent for earlier. Okay, so if you look at Haskell, it can basically, like Haskell programs can be seen, or Haskell can be seen as a category kind of, where the objects are types and the arrows are the functions between types. So you can kind of see functions in Haskell as type transformers, if you will. Endofunctors in Haskell are type constructors of kind star to star. And basically, we use the type class functor to define like what the functor for some type constructor should do on arrows. So we said that f on arrows, so here I'm introducing the 1 and 0 for the definition on arrows versus the definition on objects again. F on arrows should have the type f of 0 of A to f of 0 of B. And if we do visible type applications in Haskell, we see that fmap at the type constructor f of a function h from A to B has the type f of A to f of B. So this is kind of how we represent the definition of the functor on arrows in Haskell. Okay, so now this is kind of an involved, one of the more involved slides with a more involved level of type level programming. So we will kind of go through it slowly. So we will basically get the structural functors of for our data types by factoring the recursion out of the definition and adding it back via a fixed point. Who's familiar with like the way fixed points are used to factor out recursion at the value level? Okay, basically everyone. Okay, just then I will just do a very quick recap. Let's say we have the factorial function, which called itself in the non-base case. We can then introduce a fixed point operator, which has the type A to A to A. And basically this will kind of give something to itself as an argument. And the point is that the way that we can factor out recursion for factorial is to give it an extra argument, which is the thing that should be called recursively, and put that in the place where the recursion happens in the original definition. And then if we fix this, basically it'll always get kind of itself passed as the thing to call in the recursive position. If we look at the list data type from earlier, we can see that it looks kind of similar actually to like the term level a recursive function here, where we have kind of recursive call sites or a recursive call site. And you can actually implement, so the trick that makes this work here is that because we have a for all a here, we instantiate this a here with z to z, or it could be some other a to a type. So actually what this will read in the end is fix of type a to a to a to a to a to a, which is how you can kind of still give it an argument. And we can kind of do that at the type level, but it's not really complete. Like here, basically, this is like it's just parametrically polymorphic, so we can insert any type here. If we want to do this at the type level, then this needs to be kind polymorphic, because yeah, if I just had a fix with the kind star to star to star, then I can't replace the star in here with another star to star, which is the type of this thing that I'm calling in the recursive position, right? Because this still needs to get an argument. So I actually need to make it like so. Who has heard of type families? Okay, also almost everyone. Yeah, so as fix was like a function on the value level, we have a type family fix, which is a function on the type level, and we give this an instance actually for the kind star to star and for the kind star to star to star to star. And then we can see that the way that recursion is factored out of the list data type is very similar to the way that recursion is factored out of the factorial function here. Caveat. Basically, I kind of stumbled across this way of doing it as I was reworking this talk. So this is not actually how I'm going to be doing it. I'm doing it in a bit simpler way. You will see on the next slide how. But this is kind of the more like morally correct way of looking at it. But yeah, for the rest of the talk, we will look at a different encoding. So how I actually encode it is I just use this boring fix like type, new type, which is not a kind polymorphic. And the reason why I can use this for list is because I kind of define list pointwise. Like basically, you're forced to already give it like an argument in the definition. And the thing is like Haskell, like so, you can do like partial application however much you want with functions in Haskell, but like with types and new types and stuff, like sometimes you need to kind of satiate type constructors. There's a lot of kind of ugly stuff that happens. But in any case, like we're not going to look at the fact that there's also or like we're not going to investigate what it means for there to be a type argument to the structural list functor that is not its recursive position. We're just going to kind of pass it through and look at instances where we fix this type argument. Yes. Okay, so the way that we saw the functions earlier was we passed several arguments that were meant to replace the functors. We could also, of course, pass a tuple of functions. And now the really big brain thing happens, which is to kind of apply like laws that we know for exponentials. So we have, if we have an exponential with the same base multiplied by another exponential, this is kind of equivalent to like adding the two exponents. So the exponential in category theory is kind of equivalent to the function type from A to B. You could kind of look at it as like basically tuples of type B indexed by all of the elements of type A. And like there's basically reasons why this kind of make sense to look at it as an exponential. But in any case, you can kind of look at this resulting type as, or like, yeah, the type A plus C, you can look at this as a sum of the constructors that make up a type. And so then if you have a tuple of functions from different constructors into B, then you can refactor this as just a function from the sum type of those constructors into B. And basically to see how I'm encoding this so how I'm translating the original functions into this notation, you can you can see that we took the two functions here as arguments and are using them in a case expression that looks at the constructors of the list data type. So what I promised is that we would kind of factor out the recursion, and or like we would use the fact that we factor out the recursion to give a meaningful denotation to the business logic of the traversals. And basically the way we have done that is we expect kind of the recursive argument of the function in the position where the recursive argument of the data type goes. So basically we're now defining the business logic that traverses over a data type as an algebra of the structural functor of that data type, where instead of like in the places where in the original data type you had the recursive positions, you now have the results of the recursive arguments of your traversal. Okay, but in order to do to kind of get a functor instance for our for the actual like things that we factored out, well, we need to write a functor instance. But we don't really want to write this ourselves. So if you remember earlier, I said that you can construct functors from building blocks. Yeah, basically the list functor can be seen as the product of the constant to nil functor. That's basically like the empty list, doesn't do anything to its argument. Then the constant to A, which is like the head of the list or the identity. So this is the only place where the argument of your functor goes. And so we can write conversions between our structural functor and this generic representation of it. So yeah, this just translates nil to the constant to 0 as the first with the first tag of the union, and then cons, as I said, to the constructor in the second tag of the union. Basically, yeah, we can just get a functor instance by the fact that all of these constructors have a functor instance, and then we just translate our native data type to this generic representation and back, and do the F map on the generic representation. So basically what we have seen is that, okay, so kind of a topic that goes further that I'm not going to explore further in this talk is that fmap is like polytypic. So basically you can define it for data types that are created out of other constituent data types. And this is actually like how deriving works in Haskell, like by using the structure. You also have like derive functor, for example, which will work for many cases. And how to define other things, and the ergonomics of that is a topic on its own. So I'm not going to look into that further. And yeah, to kind of go back to category theory, we found that the map from an algebra to any other algebra, so the initial algebra, we could kind of define it as alpha minus 1, so the inverse of the function via which fa was isomorphic to itself, then the functor applied to the h, and then the psi of the target algebra. Basically, we see that the fixed point that we defined to relate the shape functor of our original data type back to the data type gives us the initial algebra. And so to go from fix of f to f of fix of f, so back from from a to f of a, since this is kind of the a of the initial algebra, we just have to define a function with this signature. And yeah, this basically just unpacks one level of the fixed point constructor. And via this construction, we basically, we just go back with the unfixed to f of a, then we f map, as we saw in the original diagram, and then we take the algebra down in our target. And that way we've basically defined this, the morphism from the initial algebra to every other algebra. Yeah, so I will quickly look at how this looks in the mutually recursive case. Basically, if I have like a mutually recursive data type, then I can have like expr, which contains like declarations, and then a declaration that can again contain an expr, for example, an expression. An example expression might be bind 3 to x, and then yeah, just do something with that. This is not really pretty printed. Yeah, and so these are now two data types, but they are mutually recursive. And the question is, how can we look at this as one functor? And the way to do that, again, I will look at how you deal with mutual recursion on the value level. So if you only have a singly recursive let, how can you have a mutually recursive declaration? So a really typical mutually recursive declaration on the value level is even and odd, where even is defined in terms of odd, and odd is defined in terms of even. So you kind of have a recursion that goes back and forth, like with these two functions calling each other. And the way to do that, if you only have like a single let, is to put these two things in a tuple. And that way you only need like one expression, but you can refer to both of these things. So we want to actually kind of put these two data types that we just saw in a tuple. And then like brief excursion to category theory again. If we have two categories, we can like construct a product category so that arrows in that category are basically pointwise arrows in the constituent categories. But sadly in Haskell, at least the functor type class is only for functors, endofunctors in Haskell itself, so you cannot kind of construct the product category. If we could somehow construct like a product of these two data types, then that, yeah, it might kind of look like this, where yeah, we kind of define them in a tuple, and then they can like reference each other again, because now instead of having like one recursive variable, or like, yeah, the structural functor, instead of having one recursive variable, it would have two kind of put in a tuple. As I said, we can't do this in Haskell. So we need to find a different encoding. And again, and I think this is kind of a theme in this talk, we just have to look at things differently. And you can look at tuples differently. You can look at an n-ary tuple. So as an exponential, this is translating. So before we saw translating arrows to exponentials, now we're translating exponentials back to arrows. You can see to n tuple a to the n as a function from a finite set of cardinality n to a, where basically each element of this finite set type will give you an index for your tuple. And basically, we kind of need to do this in Haskell. We need an index at the kind level. And to do this, we can define an enum, so a type at the value level, and then lift it via data kinds to the kind level. So we want an enum with two constructors, E and D, and these two will become singleton types and the type tag will be lifted to the kind tag, and these two constructors will become singleton types. So we can now define our mutually recursive data type, and so I'm writing it like as a type family here because this looks more like the original declaration, but type families are actually not. They don't really work. For this use case, you need to use an AST, but I thought the syntax looks nicer. Basically, you define this family at the index E. So this is now your expression data type. And so plus we saw it as recursive arguments that had expressions. So we again call this family C at the index E. Whereas the let had a declaration followed by an expression. So we call this family C at the index D, which is a declaration. And then if you look at declaration, yeah, it was like either bind character to some expression or two declarations after each other. And yeah, so again, we factored out, as we did in the singly recursive case, we factored out the recursive component. Yeah, kind of the way that you can see this as is that you're kind of given a table to configure in your recursive arguments. So this is like kind of your lookup table. You look up where you have two types in it, and it will tell you what type to use at index E for expressions, or like in the places where recursive expressions were expected, and what types to use in the place where declarations were expected. And then this will again give you a lookup table, because you've kind of now configured this structural functor with this table. But then you look up in this table the structural functor with the types that you said to put in the recursive positions. Yeah, exactly. So basically, as I said, you kind of have to transform in your head like the tuple to an indexed access to kind of some lookup table. Okay. We also need a functor for like a new functor instance for the data type we just defined. And yeah, so as we saw earlier, basically the functor that we now want is in the product category. And again, and we need to, since we don't have products, we need to kind of use this indexing. So in a product category, you have like a collection of indices, or a collection of functions, each for one for each index. And how can we define this collection? Well, you can define this as basically for all indices of your kind that you're using for indexing, you want a function from like r at that index to r prime at that index if you want to transform f of r to f of r prime. And this is basically just the pointwise notation. And yeah, so you need like I forget which language extension is it. This is yeah, rank n types. Thanks. Okay. So basically, actually, now we can just define the things that we defined earlier pointwise. This ifix corresponds to the second instance of the data family fix that I showed in the first part of the presentation. But as I said, I didn't get around to trying to translate everything into the data family syntax. and yeah, we need an we need an unfix again in order to define our catamorphism, and like the algebra we define pointwise. So algebra of f of r at index x is just f of r at index x to r at index x. And then we basically get our definition of an indexed catamorphism, where we have replaced uh, yeah, okay, so our structure functor, recall we got as an argument basically this lookup table. Then yeah, we it's basically the same as the original definition, except that the algebra now needs to be it needs to be polymorphic over the index type, and yeah, from it'll basically go from the fixed point at the index x to the return type at, or the return table at index x. And yeah, that was it for the slides, and I will finally do a tiny demo because we went through all this trouble so that we could factor out recursion out of recursive families over mutually recursive AST. So wait, see. All right. So yeah, so this is the actual ASTF definition. As I said, it's you cannot define it as a type family. You have to define it as a GADT. Yes. Um, then basically I implemented the functor instance myself because I did not use the functor kit in this case, but you can also use it for mutually recursive data types. That's basically what the paper, the multirec paper, is about. But yeah, it's basically just a question of like instantiating this at the right index. And then I can define a pretty printer as basically the const to string. So basically we have to define this as a lookup table, right? From that will give us a type for each index. And well, a pretty printer, regardless of whether we are looking at an expression or a declaration, will want to give us a string. So I just give this const. And so the business logic of the algebra is, okay, if I have a literal and the I, then I can just show it. The var was a character, so I'll return a list. If I have plus, then I want to pretty print it with an infix plus. And yeah, here's basically the place where we have factored out the recursion. We're given the recursive arguments of pretty print here on these constituents. And also especially here, yeah, where we had an expression in the bind, we're given the result of that expression, and we can basically return to our call site. And yeah, so to make this a bit nicer to write, I basically wrote some pattern synonyms so that you can pretend like you're not using the fixed point to define your original data type. Yeah, that was it. Maybe I can execute this. Print, what do they call it? Oh yeah, E2. Yeah, this is what I defined the pattern synonyms for. Yes. How do I have to call this again? I have to. Oh yeah. I Oop. Yes. So basically, this is still wrapped in the const data type. So let's. Yeah, let me. There we go. Let's see. And I put up. Come on, almost there. Yes, amazing. All right. Questions?
Who has a question?
So I have a question. It might be a little bit of a tangent, but and I can't promise that I followed everything. But so there was a point where you said that in the argument to the type constructor, you couldn't have like a product category in Haskell, so you had to like do this index tuple thing.
Mm-hmm.
Is that just with this workaround? Is there any like fundamental limitation to like expressivity by not being able to have that in Haskell, or is it just that you have to do some extra boilerplate? Like, is that a thing that could actually be implemented and would allow for expressing things?
I think basically the fundamental problem is that functor is just an ender functor in Haskell, and you want to have product categories and I don't know other kinds of things. But basically, to do that, you would have to define the class functor differently. Like basically, like the workaround that I presented, like introduces new classes for everything. But this is kind of ugly. You actually would want to have the same class for things, and that's kind of the path that the thing that I showed on the slides. I don't know where it is, but anyway, the one where I have the data family. Yes, here. This kind of goes in that direction. You have kind polymorphism, and I'm not sure if you could make like a kind polymorphic functor class. I don't know, but yeah, you have limitations, and the limitations are like that you have to write new classes and you have to like rewrite definitions, right? Like I mean, basically we had to write the definition of fixed twice. We had to write the definition of functor twice, like once kind of for kind star, once pointwise at kind k star. So in that sense, yeah, it brings you limitations, and like most like there's many functors that are not endo functors.
Any more questions?
This may be not too much topic specific, so I could follow like 50%, but since my knowledge about category theories, like really much, pretty much nothing. So, like, is there some resource where I could maybe get deep more into the category theory of this, so that like I feel I should like reread it on taking more time, because I feel really interested, and I'm sad that I couldn't follow like for the second half or so.
Yeah. Okay, let me try to remember. I'm trying to remember. Andres, the multirec paper, does it have like? Did it have a lot of categorical background, or was it mostly? But no, that's mostly the implementation. Uh, yeah, so there is a book, Category Theory for Programmers. I'm just thinking if there's a specific resource that explains the category theory of recursion schemes. I don't know. Initial algebra semantics is enough. Maybe that can help. The way that I learned this is I had a category theory course on algebra and co-algebra, and then you kind of see where this kind of stuff comes from. Yeah, and like a lot, like the classical paper. So the paper you will probably encounter when looking at recursion schemes is recursion with bananas, lenses, and barbed wire. And that one uses really non-standard notation, and it actually kind of things seem to arise out of thin air. So I do not recommend that one. I tried to read it originally and I didn't get what was happening, and then I went back to it with category theory knowledge and I just understood what was happening. So that's something to steer clear of. Yeah, I don't know. Okay.
Okay, so I'm not going to pretend like I understood everything either. But one thing that's stood out to me a little bit is so you start with this functor thing and then you traverse something, and I kind of saw the connection to like free monads where you also start from the functor, and I felt like the sequencing in a functor in a monad, so the bind operator is sequencing in a monad. Like that is some similarity to traversing the functor, or not? Maybe, I don't know. That's what I thought, at least.
I'm trying to think. I know there's like you can definitely. Wait, I'm trying to think. I don't know if there's a way you can define fmap. I think there's a way you can define fmap just if you have bind, because like monad is a superclass of functor. So like there's definitely something similar going on. I actually saw a discussion recently on like yesterday, 2 days ago on Twitter, where somebody was saying that like fix is just like the free monad without any variables or something. But
Yeah.
that was too big brain for me, so I don't really know exactly what's going on there. But yeah, I mean, monad is just the superclass functor, and you know.
Okay, I think we can agree to that.
Yeah.
I wanted to ask if we can access the slides somewhere.
Yes, actually, on the very first slide, there's a Git repo. Wait, can I go back to the beginning somehow? Let's see. Yes, so there's a GitHub repo here, and this is actually, so this is all literate Haskell. So all the code that you saw on the slides, well, almost all of it, basically like is the source code. There are some places where I used like spec to just like get highlighting, but mostly it's the direct source. I wanted to translate this into I wanted to make a blog post based on this, but the reason why I haven't yet is because I used LHS to tech to generate this, and there's this really nice thing in LHS to tech, which is you can eval things. So you can there's like a GHCI session that gets started where you can evaluate code, and so I really hate when code that's on slides is out of drift with like implementation code. I just cannot stand it. Morally, it feels wrong to me. So I want everything that's in my slides to like actually compile. And that's why if I want to say, oh, if we put this into GHCI, then we will get that. If I want to write something like that, then I want that thing that I will have in the slide to be actually the result of evaluating something in GHCI. But most like frameworks that I found for writing blog posts don't have support for that. So that is basically the reason why this is still just a slide set and not like a blog post. So if anyone has like knowledge about, yeah, I don't know, something like a Haskell plugin or something like that that will let me output eval of GHCI sessions into something, then you will see this beautiful presentation as a blog post at some point in the future.
Sorry if the question is a bit dumb, but I'm at the very beginning of this. There's a CMET library, recursion schemes, and they don't use the fix combinator, but they have like this base functor
Type family.
type family, yes, which ties the recursive definitions to the non-recursive functors,
the native data types.
Yeah, how would that differ from what you proposed with the data family?
So recursion schemes, unless it's been changed, doesn't support mutual recursion. It's just, and the choice whether you want to represent your native data type as a fixed point of your structural functor, or you want to define a type family that will map your native data type to its structural functor via some sort of template Haskell that will generate it, is just an ergonomics decision. As you saw, like we have to define basically pattern synonyms to use this this way of defining it and get any sort of ergonomics out of it. But recursion schemes, the library does not tackle the question of mutual recursion. And actually, the motivation for this talk came from the fact that when I got into recursion schemes, I was like, okay, this is great. We have this for lists and trees. And then I wanted to write a compiler, and compilers tend to have mutually recursive ASTs. And then I saw that nothing worked anymore. So yeah, basically, the recursion schemes does not do mutual recursion.
All right. If there are no more questions, then give another round of applause to Cas. That concludes our talk track for today. I should use the other microphone.